I'm very sure that the next speaker will give some advantages and good reasons to build tall buildings also with precast. George Jones is the convener of the fibCommission 6, especially for the task group for tall buildings. I'm happy to have you here, George. Floor is yours. George Jones from Ireland. Thank you.
Hello everybody and good morning. Just a bit of background on myself. I'm the convener of task group 6.7, precast concrete in tall buildings. I'm part of Commission 6 of FIB, and the task group itself brings together many of the parts of the world that use precast concrete. We have members from Europe, from North America, from Brazil, from Asia, and from Australia. So we have quite an arrangement of members. I myself, I'm a consulting engineer. I advise producers, I advise contractors, and I don't necessarily just get involved in precast concrete. So often I have to convince people that there is a benefit in precast concrete, that they should use precast concrete because they will get something from it. So firstly, we need to just sit back and see what benefits that we should actually seek from using the material. And in any project, there are 3 benefits we should be seeking. We should be firstly looking at cost. Are there any savings? Is there a certainty in the cost? Often, precast concrete, the producer will provide a lump sum price for the project. He has great control over the product, and there will be certainty in that cost. We also look for time. We would like some time savings. We would like certainty in the time. If somebody says a building's going to take a year, it takes a year. It doesn't take 2 years. Often we have investors who borrowed a lot of money. If the building overruns, it costs them a lot of money if they lose a lot of time. And thirdly, we have quality. And in precast concrete, we look to at least achieve what is required and hopefully improve upon whatever standards are imposed upon us. Certainty is a word I will use a lot in terms of benefits. Certainty reduces the risk to the owner, the producer, the contractor, whoever. If we have certainty, we know our time that it's going to take for the building, and we also know the cost of the building. And then finally on this list, any building or project, the chosen material should bring added benefits or value compared to other materials. And this often means that several materials could be chosen in a mixed construction. And I know a lot of the talk so far have been about precast concrete buildings as such, but often precast concrete is used with other materials, because often other materials give a better solution for everybody. So we all think precast concrete is a nice product, but at the end of the day, precast concrete has to be shown to bring the benefit. We don't use it because it's a nice product, we use it because it gives us a benefit. There have been a number of talks before me, and some of the material I have in this presentation may have already been covered. So if that is the case, I will move quickly between the slides. If you need me to come back, then I will come back. But I've actually split the presentation into 6 parts. The first part looks at the characteristics of taller buildings. I then look at the use of precast concrete in both mixed and precast concrete frame construction. Then the benefits of concrete as a material in general. The further benefits we can then hope to achieve by using precast concrete in taller buildings. And then finally, some case studies and examples, and a look at fib publications that relate to precast concrete in tall buildings. So looking at tall buildings in general, the previous speaker spoke about heights and stories and so on, but often there's a aspect ratio that is used to try and define a tall building. And the one that's generally chosen is 5. So on the right, you can see there we have a building that has a ratio of 6:1, 150 meters tall by 25 meters wide. And then we have a building that's 4:1. On the basis of the definition of 5, the building on the left would be a tall building, the building on the right would not be a tall building. But obviously, it's not as simple as that. The Council for Tall Buildings and Urban Habitat has come up with 3 categories to define a tall building: height relative to context, proportion, and different technologies relevant to tallness. So for instance, a 14-story building in a provincial location to the left there may be considered tall, but in an urban location in a very dense city would not be considered tall. And then we might get a slender building in an urban landscape or a building with a large footprint. So just to summarize, and I know this has been mentioned before, one of the suggestions of CTUBH is that 14 or more stories or over 50 meters could be used as a threshold. So what are the characteristics of a tall building? Well, often they have relatively small footprints, normally because of high land values and restricted space. They have a mixed occupancy with normally car parking at lower levels and then either residential or office space above. The structural engineer has to take account of the relative magnitude of the lateral loading, whether it be wind or seismic, which increases compared to vertical loading. And the cores in the tall buildings are very important, not only to accommodate lifts, but they give you a means of fire escape and provide stability. So just looking at 2 typical footprints. On the left, we have a typical office. Small footprint, central core providing stability, and a number of outlined columns that transfer the vertical load. On the right, we have a residential layout with dividing walls. You'll see that not all the walls are continued, and the tendency in Europe is to minimize the amount of structure. So we would use what they call blade columns. They would be in the area allocated for the walls. Space would be left in case later on they wanted to change the residential building into an office. It gives the flexibility to change the occupancy of the building. In any tall building, there will always be a cost premium from the fact that the building is tall. On the right, you'll see a very simple curve. The bottom curve shows the optimum design if we were designing for gravity loads only. As the number of stories increases, we then have to pay a premium for the wind and seismic forces that increase as you go taller. And you can see that premium has to be paid no matter what the material that is used for the building. So in a tall building, we have some essential components. These essential components are the cores, the floors, the vertical components that are required to transfer the loads, whether they be columns or walls, and the facade that envelops the building. These actually form the building. They're not structural component. They may not necessarily be structural components, but all these components can be provided in precast concrete. So we can deliver a structural frame that takes the form of the building with no requirement for a separate frame as you would in steel. So this gives a benefit when using concrete. I mentioned earlier that we can have mixed construction, and this mixed construction can take several forms. We could have a slip form core with precast concrete stairs and landings, in situ cores with precast concrete columns and beams, precast columns and walls with in situ floors, and so on. There's numerous combinations, and we can choose whatever combination we like for our particular building. In framing systems, there's a chart there on the right, which some of you may be familiar with. This comes from work by Kahn, I think it was in the 1970s, and splits tall building design into into 8 categories. Starting from the simplest, which is a simple framing system, up to about 20 stories, and then going on to various tube systems that can go up to 100 stories and above. So within those framing systems, precast concrete generally is recognized as being a possible solution using frame and shear wall systems for buildings up to 20 stories. For buildings greater than 20 stories, we then begin to use tube systems, and often in situ or cast in place concrete or steelwork is preferred for that. But we do have some examples later of using precast concrete. In Europe, in particular, we use a lot of walled construction for taller buildings, particularly in residential areas. And there's 3 examples here of how we can develop a framing system for particular types of applications. So on the left, we have a shear wall system. In the middle, we have coupled shear walls. And on the right, we have a frame tube with a central core. This is an example in the Netherlands. I think David mentioned this yesterday in his presentation. But this is a precast concrete coupled wall system up to 135 meters tall. So what are the general benefits of concrete? You're probably all relatively familiar with this, but concrete in itself gives us high quality and low maintenance. It gives us very good fire resistance, gives us strength, gives us temperature control and insulation, acoustic separation, durability, visual flexibility, and sustainability. Fire resistance is obviously very important, particularly in tall buildings. In concrete, we have resistance. The structure will retain its load-bearing capacity. Even in the recent disaster in London, where they had the fire at Grenfell, the concrete frame still stood up, even though the building was exposed to a very serious fire. Integrity. The structure should protect people and goods from flames, harmful smoke, and hot gases. That means that the concrete itself doesn't break down. And isolation, the structure should shield people and goods from heat. So concrete has these very good fire-resistant properties. It doesn't burn, it doesn't melt, it doesn't give off noxious fumes, it provides good insulation against heat, and it retains its strength well. So just looking at acoustic separation as one example, I've seen a lot of buildings where often strength only is considered as the primary requirement for the building, and sometimes, particularly in apartments, sound can be ignored. But sound is very important. If you live in an apartment, you don't want to hear what your neighbour's doing, either above or sideways. And you get several different types of sound transmission. You get direct sound transmission, you get flanking sound, which normally goes through joints and so on, and you get impact sound. So we normally combat this in concrete by providing mass. Mass generally will resist direct sound, and provided attention is paid to the joints flanking sound. For impact sound, we need some sort of soft covering or resilient layer to stop that sound transmitting through floors. Temperature control and insulation. Concrete has very good thermal mass, and the definition of thermal mass is the ability of a material to store heat. So if you look on the right, you will see that in general, we have these high peaks and troughs. But if we store our heat in the concrete, if you look at the blue line, that evens out a lot more, so we can control the temperature of our building and the individual rooms a lot better. So in precast concrete, we can take advantage of this. We can have our heating system within the floor slabs as shown here. Pipes are run, and we can control the temperature in the building. The pipes are contained inside the precast slab, and then we connect up to the heating system. So there's the potential to avoid air conditioning units and so on. We control the temperature in the building through the flooring system. We can also insulate the building, again, by controlling the temperatures inside by using precast concrete sandwich panels. There's an illustration on the left showing the various components of a sandwich panel, and on the right you can see a very thickly insulated sandwich panel of a photo taken in Finland, which has very, very cold temperatures. Sustainability is another possibility, and again in concrete we have low materials, readily available materials. We have low carbon, low maintenance, a long life, fully recyclable, and frequently refurbished and reused. Flexibility visually is also an advantage. This is an example of a building in California, and you can see great use has been made of the visual aspects of concrete. So they're the benefits of concrete itself, but precast concrete can also bring us additional benefits. These are a reduction in the floor cycle time in floor buildings, increased time certainty and improved completion dates, less congestion at the job site, budget certainty and value for money, quality certainty, and providing complex components often in accessible locations. So the first point on the list was floor cycle time, and this is generally defined as the time taken to construct one floor plus the vertical element supporting it. Floor cycle time is often used as a control on the construction of a tall building. The client and the contractor will want as short a time as possible with this, and cycle times are between 5 and 7 days are typical for tall buildings. So just giving you a very simple example of how we can improve the floor cycle time. Often precast columns are used to support floors in tall buildings, and that's because often they have a big impact on the floor cycle time. So for instance, if we were using precast, we might offload the elements and store them, and then we erect the element as shown there on the left. So we have 2 crane movements to install the precast column. For an in situ column, we require 6 crane movements, as you can see on the illustration on the left. So if each crane movement takes 15 minutes, then 1 hour is saved per column, considering the crane alone. And if you consider how many columns that there could be on a tall building, that equates to a very substantial time saving. This is an example of what could be saved. And on this particular example, just by using precast columns, we saved 12 weeks on the building completion date. Quality and time certainty. With precast concrete, non-compliant elements can be remade before they reach the job site, avoiding potential delays. We can also prepare mock-ups, that is full-scale models, away from the site in advance of construction to ensure that we get correct fit, finish, and we can assess the actual time required for installation. So just coming to some of the examples I have, this is a project I was involved with in London, which is Battersea Power Station. Some of you may be familiar with it. It's on the banks of the River Thames, opposite the Houses of Parliament. This was a large residential development with 1,000 apartments. There were 8 individual blocks being built simultaneously, with floor cycle times critical. The vertical elements in the floor section, in the floor cycle per block would take 3 days in precast and 2 weeks in situ. So therefore, there was 7 working days saving per floor, and for 18 floors, this required a 25 weeks saving in time. Each of the blocks contained an escape core, and a mock-up was developed to test the finish, the fit, and the timing. So this is a full-scale mock-up of a single story of one of the escape cores. So, just going back a second. So this mock-up was then achieved on site. The finished building was achieved on site. You can see there on the left the same core in the building itself, and then on the right you can see the site. We had slip form cores alongside our precast cores, so the bigger cores were slip formed and the smaller cores were made in precast. Complex components are also a potential benefit that we obtain from precast concrete. In this example, we have a tall building in London at Blackfriars. The building itself was mainly in situ concrete and steel, but they had a tricky roof detail at the very top that was originally supposed to be an in situ main frame with various steel supporting members attached to it. This proved impossible to do as a cast-in-place solution, and we finished up with a precast solution. You can see, particularly on the left here, we have a finishing element that completed 2 columns that met at a point. Would have been extremely difficult to have done in any other form other than precast concrete. This is an example of a social housing project in India that the task group visited a couple of years ago. This was a walled construction and a very interesting project. They basically made it out of solid panels. The floors themselves were solid panels that were the shape of the room. So you finished up a room with a room made out of 4 or 5 components, and everything repeated. It was a very impressive job. And you can see here them lifting the components into place. And they're using this in Mumbai as a system to achieve the social housing they require there. We can also push the boundaries with precast concrete in terms of shape. The Bella Sky Hotel in Denmark was the winner of the FIB Award for Outstanding Concrete Structures in 2014. It leans 2 ways, it twists. It's a very unique building. This just gives you an example of the type of precast that was used on this building. We had a sloping facade, but an internal building that was vertical. And just an example on the left, the load-bearing elements come down vertically, and then we have the sloping elements attached to the load-bearing elements. So why did they choose precast concrete for such a complicated building? Well, originally the building was a steel frame, but the concrete provided greater stiffness, so that was an advantage over steel. Because it was a hotel, they wanted a noise reduction at no extra cost, which they got from the precast concrete walls and floors. They had a high fire protection that they achieved with little extra cost compared to a steel frame. Okay, we could have got all those advantages out of in situ concrete, but in Denmark they chose precast concrete because it was a lower cost, and that was because precast concrete is an indigenous preferred construction in Denmark compared to in situ concrete, and there was a shorter construction period. We also use precast concrete with slip form cores, and this is quite common in a lot of urban areas. This is an example in London. We have the slip form core, we have an in situ floor, but we have precast concrete columns and walls that come up with the slip form, as you can see, and also precast concrete stairs and landings. So it just shows you how you can mix the forms of construction. This is an example, again in London at Canary Wharf, of a slip form core where they used precast concrete stairs and landings, but they installed the precast concrete stairs and landings as the slip form progressed. Often they have a problem with time because they have to complete the slip form and install the stairs and landings afterwards. In this case, the two went together simultaneously. And that was achieved because they had a gantry built on top of the slip form, which then lowered the stairs and landings into place as the construction progressed. And we have architectural shapes that we can achieve. This is the Tate Modern in London. On the left, you can see the finished building. On the right, you can see the precast concrete during construction. Facades are very important. And the trend nowadays is to incorporate everything in the panels. So in this example, you can see that the windows and the finishes are all incorporated in the panel. So the panel's put in place and you have a finished facade. Once the panels are installed, there's no further work to be done on them. We often have challenges as well in installing facades. You can see on the left where we have a guy suspended on a rope there finishing the jointing, and on the right we have a special rig to install the panels. So just finishing off, I have an example here from the Netherlands of a building that was fully precast concrete. It was 120 meters tall. It had sandwich panels. It had internal walls inside the facade, and it had floors. The panels weighed between 30 and 34 tons in this example. They had a challenge that they had to meet a specific schedule, and the use of a tower crane needed to be avoided. So in this case, they built a shed and installed the panels inside the shed. So in fact, they were working in a factory as they produced the building. So on the right, you can see from the shed, we have a vertical lift. This vertical lift of the panel then goes into the shed. It's transferred horizontally, and then it's installed in place. So they split the vertical and the horizontal transport of the elements. Often with the tower crane, you waste a lot of time lifting the element vertically, lifting it across horizontally, and putting it in place. In this case, because it was split, they saved that time, and they managed to reduce the cycle time down to 5 days. They had little influence from wind on the construction process because they were working inside the shed. And the shed also enabled non-structural construction to start immediately after the precast. It's very clean and dry, and obviously reduced risk of disruption because of weather and so on. I think yesterday David touched on dry joints and the way we install walls in Europe. You can see here they use what they call an overlapping panel system. The weight of a panel above holds down the panel below, and it's very similar to a masonry construction where we use the stretcher bond of the masonry to stabilize the whole facade. So just finishing off on some FIB publications. There is already a state-of-the-art report on tall buildings. This report covers the design of buildings in concrete, not necessarily precast, but it gives you the design methods to assess a building that is built in concrete, a tall building built in concrete up to 300 meters tall. We are now involved in the preparation of our bulletin, Precast Concrete in Tall Buildings. We have 12 chapters. We've split them into the type of systems that can be used, and then the elements that form those systems, and we go into some detail then on connections and how we achieve a solution in precast concrete for tall buildings. And we finish off with a lot of case studies from across the world. So we're looking at examples from all of our members, including China. Thank you for your attention. Thank you.
Thank you, George. Please stay on the stage. Thank you. It was very interesting to see how easily you identify the advantages just by calculating, for example, just the columns. And yes. The columns are only one piece.
Yes.
So there are many more precast elements to be used in the tall buildings. So even your calculation can be easily multiplied to gain all the advantages. Are there questions to George Jones or maybe to Professor Chang with regards to the Chinese or European way of building tall buildings? Do you have a question? No. Okay. So, well, please, one question from the US.
I'm curious if the Chinese think that there's a possibility of using the slip-form core system for the lateral stability of tall buildings. I think there's a great advantage in using that, and I wonder if China will develop that in the future.
Well, that's a question I can't answer, but I would say that the slip-formed option is probably the most used in Europe. The examples that were given yesterday in Belgium, I think that system uses a slip-form core, and the slip-form core works in conjunction with precast floors, columns and walls that are outside the core. So I think it's a very good form of construction. And I think a lot of the issues that I've heard that they have in China regarding cost and time may be solved with using a mixed construction and using the benefits of cast-in-place concrete in conjunction with the benefits from precast. You often find that the best solution is one that uses both.
Well, and maybe coming back to the time, in your presentation there were very nice pictures where you could see a single wall element, and you could see all the joints that you need to have to close and to fill with concrete. And this is obviously time consuming, which we avoid in Europe. Well, okay, thank you very much. If there are no more questions, we have a small coffee break and we'll continue with presentation.